So we are going to be working on adding in energy and calculating that today. So if we look back at our constants that we started with yesterday, these were those constants that we worked with. Yesterday's equation was this equation right here. Okay. Today's equation, we're going to use this sometimes, and we're going to use this as well. This H in this equation is Planck's constant. So that is this guy right here. So that is your H for Planck's constant. Okay. What's wrong? Good. Okay. So this is when it asks for H, this is what we're going to be using. We may have a couple problems like this too. We'll see. All right. We've got, we did these yesterday. So we're down to here. So we're adding in that energy. So calculate the energy of a gamma ray whose frequency is this. Okay. So I'm going to use this equation this time. We are calculating energy, which is this first guy right here. So that's what we're calculating. So I don't need to rearrange this at all. My energy then is going to equal Planck's constant. So I'm going to go and grab Planck's constant from that box that I gave you the known values for. And I'll give you those on an exam. You don't have to know those. Okay, you don't have to memorize those. You don't have to memorize the equations. I'll give those to you as well. So I'm going to grab Planck's constant. It was 6.626 times 10 to the negative 34 joules seconds. I am then going to multiply that by my frequency. Maybe that won't show up. I'll do that in green. My frequency, which is V here, I'm going to multiply that by this. Remember, the units for frequency, instead of hertz, we can write down 1 over seconds. Okay, so that's what I'm going to write down because I want to cancel these seconds out. So I'm going to multiply this by 5.02 times 10 to the 20th. And that is 1 over seconds. So what happens to my seconds then? Right, they're going to cancel out. So my seconds are going to go away. That's going to leave me with joules, which is a unit for energy. So that's good. That's what you want to happen. So see if you can come up with the correct answer to this problem. I don't know where my calculators went off. There. It ran off somewhere.
We got hooked up for like there's the last one. Use a battery. It does. It's a quad battery track. It's bad. I'll make it. I hope. See. I don't know how bad it is. That was a triple F.
Sorry, we got you.
It's a quad triple.
Seriously?
It's like a liver transplant.
It's like a liver transplant?
Yeah. Or should you tablet?
His battery? Can you look at his battery?
All right. Hopefully you ended up with 3 sig figs, so 3.33 times 10 to the negative 13. And what are my units? Joules. Anybody not get that? I need to help you with a calculator. Did anybody not try it? You should be trying this and playing along.
I just didn't know.
All right, ready for the next one? They want to know the difference in energy between a photon of violet light and red light. Okay, so we're going to do an equation over here for red light, and we're going to do an equation over here for violet. It's as close to violet as I can get on here. Okay, so I'm going to start out with my energy equals, and I'm going to put in my Planck's constant. So that is 6.626 times 10 to the negative 34 joules seconds. I'm going to multiply that by the frequency of light. This is the violet light here. So that is going to be 6.80 times 10 to the 14th hertz, which is, what does hertz equal? 1 over seconds. So my seconds cancel. And my energy, there we go. My energy then is going to equal 6, 12, 14. I ended up with 3 sig figs, so 4.51 times 10 to the negative 19th. Units are joules. Yep. That's Joule, in case you're wondering. All right, the next one then, we're going to figure that out for the red light. So same setup as before. I'm going to multiply that by our red light here. And that's 1 over seconds. That's 4.3. And you should have gotten 2.8. Oh, 2.8. Yep, that's right. 2.8 times 10 to the negative 19th. And again, joules. And that's 2 sig figs because your measured amount was 2 sig figs. Okay, questions? All right, yes. Oh, yeah, she's right. We subtract because we want the difference. So we're going to take this guy minus 2.8 times 10 to the negative 19 joules. And the difference then should be I ended up with 1.7 times 10 to the negative 19th, and that would be joules. You playing along? You getting this? Yes, sir. I don't look on the front cover of your packet. I want to say it's the third or fourth. Third, I mean, yeah. If you go back up to your sheet here at the beginning, it's this constant right here. This is what H is. This is the equation we've been using. Good? Yeah. Okay. All right. You ready? You ready? You ready? Let's see here. That's the one we just finished. So you ready for the next one then? All right. The next one is going to be multiple parts. Okay. So they're giving us a wavelength, and then they want us to do energy. Well, these are our equations. We have C equals wavelength times frequency, and we have energy equals Planck's constant times frequency. So these are our two equations. We can't just do this by using one of these. We need to use both, because we're starting with a wavelength, and then we're moving, and we want to actually solve and end up solving for energy. But to solve for energy, what do we need? Frequency. So you've got to solve for frequency here first, and then sub that into this equation. But before you can solve for wavelength, what do we need to do? Convert it into meters. Okay, so see if you can convert this into meters on your own. You should be able to do that after your practice from last night. Okay, all right, so you should have ended up with nanometers down here, meters up here. And if you use that chart that I showed you yesterday, there's one of these and 1 times 10 to the 9 of these. So that should equal 4.9 times 10 to the negative 8 meters. Okay, now this is your wavelength. You are going to solve for frequency. So frequency is going to equal C over wavelength. You've got your wavelength, solve for frequency, and then dump that into here and solve for energy. All right, how'd you do on those? Killing it? Doing good? Now, this might be slightly off just a teeny tiny bit because I grab the figure from here and just bring it down with this calculator. But if you're clearing it every time and just retyping in certain ones of it might be off just a little bit. This should be 10 to the negative 18, though. And this should be in the ballpark of where I'm at. Okay? Everybody cool with this? Anything not making sense here? Before we move on. We're moving on. Yes? All right. We have an ultraviolet lamp. This lamp, the energy of a single photon of radiation is this. They want to know the frequency, the wavelength, and then the energy of 1 mole of these in kilojoules per mole. This is going to involve some dimensional analysis. Okay. This is the last one for the day, but this is kind of a doozy. All right. So first thing we want is we want to solve for frequency. So frequency, if we're given energy, which equation are we going to use? This guy or this guy? Equation 1, equation 2. Which one are we going to use with this information? Equation 2, because it's energy, and this is energy. See how we pick that? Okay. Now, we're solving for frequency. So how are we going to get this guy by itself? Divide what? By what? What am I going to divide here? Right. Energy divided by H. Okay. So frequency is going to equal my energy over Planck's constant. So let's solve for that real quick. 6.056 times 10 to the -16 joules. And that is going to be Planck's constant. All right, my joules end up canceling. And that's going to leave me with what units? Not seconds. No, hertz. Or you could do 1 over seconds. That seconds is on the bottom line, though. Okay, so don't write down seconds because it's not seconds. It's this many things happening every second. That's what that means. We're having this many waves pass by every second. And I got to calculate how many that is. Just give me a second. 6.056 negative 16. All right. So every second, I'm having this many waves come by. I got to have 4 sig figs. 40 times 10 to the 17th. 1 over second. So I've got this many waves moving past every second. That's what that means. Good? Okay. All right. So that was letter A. This is my frequency. Now they want us to take that frequency and solve for wavelength. So wavelength then, wavelength is going to equal the speed of light over my frequency. So speed of light is 3.00 times 10 to the 8th meters per second divided by 9.140 times 10 to the 17th, and that's 1 over seconds. So my seconds cancel. That's going to leave us with meters for our unit. And I end up, I want 4 sig figs. So 3.282 times 10 to the negative 10. And that's going to be meters. That's pretty tiny. Get it? Did you even try? All right. Okay, so this is energy per photon here. Okay, you guys might have to go off into your margins here. I'm going to erase some of this stuff. Anybody still need any of this up? I just have to clear out some room here so we can do some fun dimensional analysis, you guys. I know how much I love that. Okay, you guys should have a margin to be able to work with here. All right, so this is 6.056 times 10 to the negative 16 joules per 1 photon. I got this from this. This says a single photon has this energy. Everybody caught up and happy with that before we proceed? All right. So we need to attack this on 2 different fronts. Front number 1 is we need to get this into kilojoules. Front number 2 is we need to get this into moles. It doesn't matter which one you start with, as long as you hit them both. I'm going to start with the one that you're probably a little more familiar with, which is joules and kilojoules. Okay. King Henry doesn't usually drink chocolate milk. Okay. So I am at joules and I'm going to kilojoules. When we're converting and creating our conversion for this, wherever I'm at on the line, I make the bigger one 1, and then I figure out how many of these are in that by moving my decimal. So I need to move my decimal 1, 2, 3. That means that I need to add 3 zeros. So there is my conversion factor. That's going to give us kilojoules per photon. They didn't want to know kilojoules per photon, though. They wanted to know kilojoules per mole. Okay, so I need to get rid of photons. Does that mean that photons are going to go on the top or the bottom of my grid here? Top, because anything that you want to get rid of goes on the top. I think I misspelled that. No, I didn't. I had that right. No, I did. I had an extra N in there. Let's start that over. Okay, let's try that again. PHO, photon. There we go. All right. Now, I'm going to take photons and we're going to go into moles here. And we've got to get a conversion factor for this. Okay. If you go back up to this guy, right here is your conversion factor. So 1 mole is going to equal this many photons. See where I took you back to? You're familiar with this slide? All right, so we're going to dump that data into here. So for every 1 mole, I have 6.02 times 10 to the 23rd photons. Now I'm just going to work my dimensional analysis. I'm going to multiply across the top, multiply across the bottom, and then I'm going to divide those two. Five, 6, negative 16 times 6.02 to the 23rd divided by 1,000. My calculator kicks this back to me. We're going to talk about how we're going to write that down. That's what my calculator gave me for an answer. How many sig figs should I have in my answer? 4. This was my measured amount right here. It has 4 sig figs, so I need 4 here. So I can do one of 2 things, okay? I can round this off, keeping placeholders, and write this as 64600 with no decimal. Or I could do 6.646 times 10 to the 1, 2, 3, 4, 5, 5th. And that is going to be kilojoules per mole. And that's as hard as a problem gets. Good? Everybody happy? Not really? No. All right. Well, 5-3 is the homework for tonight. It is due tomorrow.